Namaste to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on zeros, singularities and poles. Lecture number 4, in which I will prove some theorems on zeros, singularities and poles. Also, I will give the concept of residue at a pole. Now we define residue at a pole. Let Z not be a pole of order m of function of z, then function of z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus b1 by z minus z naught plus b2 by z minus z naught whole square plus plus bm z minus z naught whole to the power m. This is in a Lorentz series. The principal part contains finite number of terms where bm not equal to 0. Then b1 is called the residue of function of z at the pole z equal to z naught. Now we prove theorem 1. The statement of theorem is, if a function of z has a pole of order m at z equal to z naught, then the function phi defined by phi z equal to z minus z naught whole to the power m function of z has a removable singularity at z naught, and that function of z naught not equal to 0. Also, the residue at z equal to z naught is given by m minus 1th order derivative of function phi at the point z equal to z naught by factorial m minus 1. Now we prove this. Since given that function of z has a pole of order m at z equal to z naught, therefore function of z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus b1 by z minus z naught plus b2 by z minus z naught whole square plus plus bm z minus z naught whole to the power m, where bm not equal to 0. This function has been expressed in Lorentz expansion, in which the principal part contains m number of terms, that is finite number of terms, and the coefficient of last term bm not equal to 0, and modulus of z minus z naught greater than 0, less than r greater than 0. Also given that function phi of z equal to z minus z naught whole to the power m multiply function fz. Let this is number 1 and this is number 2. from 1, we get that residue at pole z equal to z naught is B1. This is number 3. Multiplying both sides of 1 by z minus z naught whole to the power m, we get z minus z naught whole to the power m function f z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus m plus b1 z minus z naught whole to the power m minus 1 plus b2 z minus z naught whole to the power m minus 2 plus dot 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 plus bm implies that this is phi z equal to sigma n equal to 0 to infinity a n z minus z naught whole to the power n plus m plus b1 z minus z naught whole to the power m minus 1 plus b2 z minus z naught whole to the power m minus 2 plus dot 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 plus bm. Let this is number 4. Taking limit z tends to z naught in both sides, we get limit z tends to z naught phi z equal to, in right side if we put z equal to z naught, this is 0, this is 0, this is 0, only remains bm. This is number 5. From 4, it is clear that phi z is a power series. For modulus of z minus z naught greater than 0, less than r greater than 0. Therefore, function of z is analytic in this region, implies that function of z is continuous in this region. Therefore, limit z tends to z naught function of z equal to, function means phi z equal to phi z naught, implies that phi z naught equal to limit z tends to z naught phi z equal to bm, using 4. and given that Bm not equal to 0 implies that phi z not equal to 0. This is number 6. This is number 7. In 4, we see that the principal part of phi z is 0, means there is no term in the principal part of 4. Therefore, phi z equal to z minus z naught whole to the power m fz has removable singularity. Since phi z is analytic in modulus of z minus z naught greater than 0 less than r, therefore by expanding this in Taylor series, we get phi z equal to phi z naught plus z minus z naught first order derivative of phi at the point z equal to z naught by factorial 1 plus z minus z naught whole square second order derivative of phi at the point z naught by factorial 2 plus dot 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 plus z minus z naught whole to the power m minus 1 m minus 1th order derivative of phi at the point z equal to z naught by factorial m minus 1 plus dot 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 dot. Let this is number 8. Comparing 8 with 4 and by equating the coefficient of like power of z minus z naught, we get coefficient of z minus z naught whole to the power m minus 1 equal to b1 equal to here in 4 this is b1, in 8 this is phi m minus 1th order derivative at the point z naught by factorial m minus 1 implies that this b1 is the residue of the pole, residue at the pole z naught equal to m minus 1th order derivative of phi at the point z equal to z naught by factorial m minus 1. Therefore, proved. Here we have an important note. If z equal to z naught be a simple pole of function of z, then function of z equal to sigma n equal to 0 to infinity an z minus z naught whole to the power n plus b1 by z minus z naught. In principal part, we get only one term for simple pole. Therefore, residue of the pole at z equal to z naught is b1. Therefore, limit z tends to z naught, z minus z naught fz equal to limit z tends to z naught phi z. And we know that this is analytic and also continuous, so this equal to phi z naught, and this is equal to b1. In the case of pole of order m, phi z naught equal to bm. Here phi z naught equal to b1, since in principal part we have only one term. Therefore, when z naught is a simple pole, then residue at z naught is phi z naught equal to limit z tends to z naught z minus z naught fz. Now we prove the next theorem. Theorem is, let function of z fz be a function such that for some positive integer m, a value phi z naught exists with phi z naught not equal to 0, such that the function phi z equal to z minus z naught whole to the power m fz is analytic at z equal to z naught. Then fz has a pole of order m at z equal to z naught. Now we prove this. Given that phi z equal to z minus z naught whole to the power m fz is analytic at z equal to z naught. Also, given that phi z naught not equal to 0, let this is number 1 and this is number 2. Since phi z is analytic at z equal to z naught, implies that phi z may be expanded in Taylor series phi z naught plus z minus z naught, first order derivative of phi at the point z equal to z naught by factorial 1 plus z minus z naught whole square, second order derivative of phi at the point z equal to z naught by factorial 2 plus plus z minus z naught whole to the power m phi, mth order derivative of phi at the point z equal to z naught by factorial m plus implies that phi z by z minus z naught whole to the power m equal to phi z naught by z minus z naught whole to the power m plus 1 by z minus z naught whole to the power m minus 1, first order derivative of phi at the point z equal to z naught by factorial 1 plus 1 by z minus z naught whole to the power m minus 2 second order derivative of phi at the point z equal to z naught by factorial 2 plus dot 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 plus phi m minus 1th order derivative at the point z equal to z naught by z minus z naught factorial m minus 1 plus sigma n equal to m to infinity phi nth order derivative by factorial n z minus z naught whole to the power n minus m implies that this is left side is phi z by z minus z naught whole to the power m is fz using 1 phi z naught by z minus z naught whole to the power m plus first order derivative of phi at the point z equal to z naught by z minus z naught whole to the power m minus 1 plus second order derivative of phi at the point z equal to z naught by z minus z naught whole to the power m minus 2 multiply factorial 2 plus dot 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 plus phi m minus 1th order derivative at the point z equal to z naught by z minus z naught factorial m minus 1 plus sigma n equal to m to infinity nth order derivative of phi at the point z equal to z naught by factorial n z minus z naught whole to the power n minus m. Let this is number 3. Here we see that number of terms in principal part equal to m and given that phi z naught not equal to 0, this is not equal to 0, so we get that z equal to z naught is a pole of order m of function of z. This is the highest power of z minus z naught at the denominator, and this part is principal part. So this z equal to z naught is a pole of order m. Also, the coefficient of one by z minus z naught equal to m minus 1th order derivative of phi by factorial m minus 1. This is m minus 1th order derivative of phi at the point z equal to z naught by factorial m minus 1 this is residue of the pole Z naught. From this theorem we get an important note. If fz equal to phi z by z minus z naught whole to the power m, where phi z is analytic at z equal to z naught and phi z naught not equal to 0, then fz has a pole of order m at z equal to z naught. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.